So when we take a look at torque problems, it's important to first draw a clear picture, then draw a free body diagram for each object in question, identify the axis of rotation and the torques about it, apply the sum of the forces, or some of the torques rather, like we did with some of the forces, and then bring it all together. So if we look at an example here, let's go ahead and do a quick example. Let's say this is 5 meters, and let's say we push here with 3 newtons of force, and then let's say, and that at the 5-meter mark, and then let's say over here we push at the 4-meter mark 3 newtons. Okay, 3 newtons over here, and then 5 meters for this one. When we add up the sum of the torques, so we'll look at some of the torques here. We're going to have, in this case here, with this bottom one, counterclockwise torque. So that would be positive torque from the 5-meter mark. And then this one at the 4-meter mark is going to cause a clockwise torque. So that would be plus the negative torque caused by the one at the 4-meter mark. And then we can get the total. So we have the 3 Newton one times 5 meters plus the negative 3 Newton one times the 4-meter one, and we end up getting 15 plus negative 12. The total amount of torque would be 3 Newton meters positive. So what that means is the this one here, the one pushing at 5, is actually going to make it go this way. And so the overall torque, if we just had one torque instead of all of those, would be the equivalent of that. Now we're going to take a look at a double pulley that has 2 weights hanging from it. And we want to find out what the net torque is. So the axis of rotation is right here in the middle. And these two wheels are interconnected where the 10 kilogram mass is pulling on it to make it, you want to try to go this way, and then the 2 kilogram mass is want to make it go this way. So we want to find the net torque of these, and we want to figure out what direction the pulley will rotate. So if we take a look at the overall torque here, we can look at both of these. Let's take a look at the 2 kilogram one first. So this is going to be pulling straight down on it here, and we have a lever arm here, 3 centimeters, 0.03 meters. And what kind of torque will this cause? Well, the mass is going to be pulling down like this, so it's going to cause the wheel to turn like this, and that would be in a clockwise manner. So that's going to be some negative torque from this one. Let's take a look at the 10 kilogram one. Well, the lever arm for this one is 2 centimeters, so 0.02 meters. And it's going to cause the rotation of the wheel to go this way, which would be counterclockwise, which would be a positive torque. So when we add these two up, they're going to be fighting against each other, and we can figure out what the overall torque is by adding those up. So why don't you go ahead and pause the clip, calculate what the torque will be for the 2 kilogram mass and the torque from the 10 kilogram mass, and then when you're ready to check, you can hit play to continue. Okay, so we know that the force of gravity on both of those are what the force is on that, and we've got 19.6 newtons for the 2 kilogram mass, and then 10 kilogram mass, we've got 98 newtons, pulling down on it. We add up the two torques. The torque from the 10 kilogram mass is positive. The torque from the 2 kilogram mass is negative. And when we multiply those out times the forces, we would get positive 1.372 Newton meters. And positive means counterclockwise. So this mass is going to win, making it go counterclockwise as it goes. Okay, so let's take a look at this one here. We've got two children on a seesaw, and we'll call, well, we have the seesaw with the lever arm here in the middle, or the axis of rotation, and we've got the 60 kilogram child we'll place on the left hand side over here, and the 45 kilogram child over here. So if we look at the forces, we have the force of gravity of both of them, and that's what's going to cause the torque about this axis here. And so the kid 2 here would cause a torque of this whole system to be clockwise, and then the torque on this would be counterclockwise. So when we set up the oh, and then we have the force of gravity of the beam, and the force of gravity of the beam is right smack in the middle, so the lever arm for that is 0. There's not going to be any torque due to the beam. And when we set up the sum of the torques, we have mass 2 on the right side over here, which is our clockwise torque, and that's negative. And then we have our mass 1 over here, the positive torque. And yeah, so why don't you go ahead and pause the clip. You can calculate out what the torques are and get the final amount, get the magnitude of the net torque in part A, and then you can figure out the direction in part B. So go ahead and pause the clip and you can try that, and you can hit play when you're ready to check. Okay, so we've got our two lengths. The force of gravity on kid 2 over here is 441, and then 588 for kid 1. When we add those up, get a positive 367.5 Newton meters, be a counterclockwise torque because it's positive. So, the seesaw is going to go around like this, which makes sense because the person on the left-hand side has more mass than the person on the right, and will cause a counterclockwise torque. Okay, so now we're going to look at where we have a balanced situation where the seesaw is going to be balanced, where we add up the torques and they add up to be 0. And this is called rotational equilibrium. We've looked at translational equilibrium. Translational is, left to right. And so this would be like, we have a block that we're pushing on this way and this way. And let's say those are equal to each other. It would be in translational equilibrium. But in this case here, rotational equilibrium is where the torques add up to be 0. So let's say we have a 5-meter seesaw. The fulcrum's at the middle. 45 kilogram child is all the way at one end. Where must the 60 kilogram child be if it's to be balanced? So in other words, we have the 45 kilogram child. We'll go ahead and put them on the left. We have the 60 kilogram child on the right with a certain lever arm, and that's what we want to find out. Where would the 60 kilogram kid need to sit so that the two torques balance out? So what I'm going to have you do on this one is I'm going to see if you can work this one through. The only thing that I'll help you with here, we've got the two forces there. We're going to add up the torques to be 0. And so you can write out, we have the positive torque from the 45 kilogram kid, the negative torque from the 60 kilogram kid, and they're going to add up to be 0 because they're going to be balanced, translational equilibrium. So yeah, why don't you go ahead and solve for what this will be. Make sure you leave this in variable form. It's going to be the force times x, and then you can work out the math there. So go ahead and hit pause and go ahead and try this, and when you're ready to check, you can hit play to continue. Okay, so we can add that over to the other side, and the 60 kilogram kid would need to sit at 1.875 meters, which would be, that far from here. The 5 kilogram kid is sitting 2.5 meters from the center. And so that makes sense. The 60 kilogram kid would have to sit closer than the 45 for the torques to balance out. Okay, so on this one, we have a 5-meter long seesaw. It's balanced on a fulcrum at the middle. 45 kilogram child sits all the way at one end, and then 60 kilogram kid on the other. We want to figure out where the fulcrum needs to be placed to attain a balanced situation. So let's go ahead and assume the 60 kilogram kid is on the right hand side, and then the 4 kilogram or 45 kilogram kid will be on the other. And then here's the fulcrum um, here, and the question is, where do we need to place that? So what we can do is, establish this in variable form. We can say, okay, how far from here, from the 60 kilogram kid, will we need to put the fulcrum? And what would happen then, if we have the 60 or 45 kilogram kid on the other side, we'll have that, and then we'll have a certain length over here as well, um, and that'll be good. So um, in this case, we have the force of gravity of the 45 kilogram child over here. We have the 60 kilogram child over here. We have the fulcrum, and then we have something that we haven't had to deal with yet. We know that the fulcrum here is going to be closer to the 60 kilogram kid to make it a balanced situation, right? Where all the torque added up will be 0. So it turns out that the beam itself will actually have a torque, because now we have a lever arm. Up to this point, we looked at fulcrums where they're located at the the force gravity of the beam itself, and so now we will have that. And so as we set up the sum of the torques here, we're going to have to consider, where is the force of gravity going to be? Well, we know that the force of gravity of the beam is right in the middle, right, which is 2.5 meters in the middle of the 5-meter long seesaw. So what we can do in variable form is we can have the force of gravity of the beam 2.5 meters minus x being how far the fulcrum is from the edge. And then that will give us this length right here. 2.5 meters minus whatever the x is will give us the length from there. So likewise, when we set up, the 45 kilogram kid, where this will be is, x is again representing where the fulcrum is based on where the kid is. So it would be 5 meters, which is the entire length of the seesaw, minus x. And that will give us this length right here in black. And that's what we need for our lever arm. So when we set up our torques, we can think about, the 60 kilogram or the 45 kilogram kid here will cause a rotation like this, which would be counterclockwise positive here. The beam, right? The beam is also going to be a clockwise torque, because acting about this is the rotation of axis, clockwise movement there, or counterclockwise rather. And then the 60 kilogram child will be a clockwise torque, therefore positive over here. And so we've got that. We'll set it up in variable form. So we have the force of gravity of the 45 kilogram child times 5 minus x. Remember, that's the lever arm for the 45 kilogram child. The 60 kilogram, 2.5 minus x. And then the beam, 2.5 multiplied by 2.5 minus x for the beam. And then the force of gravity child with a lever arm of x there from where the fulcrum is. And so our only unknown is x. And we place our values in there. Force of gravity of the 45 kilogram child is 441, and then 980 for the beam, and then 588 for the other child. And we can distribute there inside the parentheses, and then solve for x. And so 2.371 meters is where the fulcrum would be. And so it would be on the right-hand side again of the beam there. And that would make sense. Actually, everything would be balanced out at that point. Okay, so on this one, we have a 10-meter long wooden plank, mass of 209 kilograms on a flat roof with 2.5 meters extended beyond the roof's edge. The question is, how far out on a plank can an 80-kilogram man walk before he's in danger of falling? So on this one, we have a couple different dynamics going on, but still looking at the torque involved. So if we draw the man there, we can draw the force of gravity. There, the axis of rotation will be right on the edge of the building, right? So the plank can rotate, and it would be about that edge. We may have the force of gravity of the beam right in the middle, and yeah, we want to figure out, how far out can the person go. So if we think about that, how far out on the plank, that would be how far from the axis of rotation that's in question, right? So how far is X? So what we can do is we can say, okay, how far would it be safe? How big could X be? And then we can compare that to, here at the edge of the ramp, and we can find that. So what I want you to do is go ahead and set up the sum of the torques equals 0. Go ahead and write out what kind of torques there are, positive or negative, and then see if you can place the values in there in just in variable form for the two torques involved, and then yeah, see if you can figure out how far the person can go. And then when you're ready to check, you can hit play to continue. So go ahead and pause and then try that, and then hit play when you're ready to check. Okay, so we've got 2.5 meters from for the force of gravity of the beam, because we know it's 10 meters long and it's extended 2.5 meters out. So therefore, there's 2.5 meters left of the center of mass of the beam, and so we have force of gravity of the beam times 2.5 plus negative force of gravity of the man times x there, and the sum of the torques will equal 0, and 6.531 meters. So theoretically, what the person would be fine coming out at least to the 2.5 meters, and really could go all the way to 6.531 if it extended all that way. So the person would be